Chapter 25, Problems. I think first we'll look at all the equations in this chapter. The first one that we had was electric current, I. Actually, it stands for intensity of electric current. That's why they use I. Is Q by T or dQ by dt, either way. Is charged by time. Q is charge in coulombs, time in seconds. You would get current in coulomb per second, which is also called an ampere. And the symbol for ampere is A. And then we have Ohm's law, according to which the current flowing, the current flowing I is voltage by resistance. And voltage is measured in volts. Resistance is measured, so R is resistance, measured in ohms, symbol omega, and I is current measured in amperes, A. And then resistance actually is given by the formula rho L by A, where R is the resistance in ohms, L is the length in meter, area A in meter squared, and rho is called the resistivity. It is a constant for a particular material. And when you rearrange this formula, you get the unit of rho as ohm meter. It's not ohm per meter, it's ohm meter. Then we also see that the resistance or the resistivity changes with temperature. As the temperature increases, the resistivity also increases due to an increased number of collisions. And the relation resistance at T degrees Celsius is equal to the resistance at 0 degrees Celsius times 1 plus alpha T minus T naught. So once again, resistance is in ohms. That is the resistance at T and at 0 degrees Celsius, both in ohms. T is the temperature, which could either be in Celsius or Kelvin because you are talking about the difference there. And alpha is a constant for every material again. It is called the temperature coefficient of resistance. The temperature coefficient of resistance. And its unit, if you rearrange that, its unit is per degree Celsius or per Kelvin. Well, then we have power. Power is the product of voltage and current. Voltage is in volts, I, current is amps or ampere, and power is in watts. There are two other formulas for power. One is power is equal to I squared R, or P is equal to V squared by R. Depending on the situation, you use any one of these formulas. And then when you look at the microscopic view of current, you have a formula for current as I is equal to N A V or VDE. Now remember that N is the number of electrons in 1 meter cube. Number of electrons in 1 meter cube. A is the area of cross section. And V is the drift velocity of the electrons, which is really small. So that's the drift velocity. And obviously E is the charge of the electron, which is 1.6 times 10 to the negative 90 coulombs. Now from this formula we could also go to the formula for current density. Current density is defined as the current flowing through unit area. So you divide by A, and from the above formula you would get NVE. Remember that current density is a vector. This can be also proved to be equal to sigma E, where sigma is called the conductivity, and sigma is the reciprocal of resistivity, rho. So these are the combinations and these are the formulas in this chapter. On the second one, the resistance is 12 ohms at 20 degrees Celsius and 140 ohms at an unknown temperature. So that's the equation. Make T the subject, rearrange, substitute the numbers, and get the answer as 1797.8 degrees Celsius. In the third one, you have to find the ratio of the resistance of an aluminum to a copper wire. And the formula is R is rho times length by area. So you make the equations for both aluminum and copper and divide. This is what you get. The lengths are 10 and 20. The area of cross section is pi r squared. So the millimeter has to be changed into meter. And once you square that term and plug in the values for the resistivity of aluminum and the resistivity of copper, you finally get 1.232. It's just a ratio, no unit. In number 4, you buy this light bulb in Europe, but you want to use it in the US. Now, remember that for the light bulb, the resistance does not change. So that is what we try to find first using the formula for power. It was built to be used at 240 and would produce 75, so its resistance is 768 ohms. But in the US, the voltage is only 120. So once again, use the formula for power. And find the power out. Remember, the resistance doesn't change. And that's why it's 768. And you see that it's only 1/4 of the actual power that this could have produced, and that's because the voltage is become half and the power is dependent on the voltage upon its square, in fact. So that's why you got it. Number 5. This is a particular problem where 85 ampere hour means you could use this car battery for 85 hours drawing 1 ampere current, or you could use it for 1 hour if you were trying to draw a current of 85 amperes. So the product of the current and time in hours must be 85. So that's the formula for power. Rearrange it, and the power is work over time, work is energy. That's what I put. So voltage times current times time. Time must be in seconds. And you get this 3.672 times 10 to the 6 joules. It's the formula for heat produced. You don't need it here. So that brings us to number 6. It's always an advantage to transmit electricity at high voltage, because at high voltage the current would be really low and the heat produced would be really small. So which means that there is less power wasted during transmission. So the power is 620 kilowatts. That's the voltage required. Resistance is 3 ohms. And use P is VI, make I the subject and calculate the current. So you get 51.67 amperes. And in this case, the power wasted would be I squared R, which is the square of the current times the resistance. So you would be wasting 8,009 joules. But if it was transmitted at a voltage of 50,000 volts, then the current would have been much less. The current would have been 12.4 ampere, and the power wasted would be I squared R again. And that's only 461.3. So you see the difference in the power wasted when you transmit electricity at a lower current, which means higher voltage. So in this case it is 7,547.7 watts. In the 7th question, the length is given, the current, the voltage applied. You have to find the resistance. So first let's start with the resistance. Let me remove that. Resistance is voltage by current. So just divide. Both are in millivolt and milliampere. So 10 to the negative 3. And it's 11 by 375. That's not a T. That is 11 by 375 ohms. And then the B part, to find the resistivity, use this formula. Area is pi r squared. And you get the resistivity as 1.589 times 10 to the minus 8. And then to find the number of free electrons per unit volume, we use the formula I is NAVE, and you get N is equal to I by, and find the number of free electrons in 1 meter cube. I think I'm going to write that again, a little bit more clearer. pi times the area, radius squared. That's the velocity times the charge of the electron. When you calculate, you get 8.776 times 10 to the 28 electrons per meter cube. In the eighth one, you have the battery and you have the internal resistance, little r, connected to the starter, which is having a resistance, capital R. The total resistance in the circuit is R plus R. And so the current is E by R plus R, where E is the maximum EMF that it can produce, which is 12. Okay, so you get the resistance of the starter first, and then plug it back into the first equation, which is this one. Rearrange and calculate the internal resistance. The internal resistance is the resistance inside the battery, because the current that flows through the outside of the circuit should also flow through the inside of the battery, and it's going to provide a resistance, which in this case is 0.048 ohms. Number 9 is the same type of question, but here you have two bulbs, and they are connected in parallel. So first you find the resistance of the bulb, 48 ohms, and when you have two of these in parallel, you're going to go 1 by R is 1 by R1 plus 1 by R2, which when you calculate, you get it as 24 ohms. Simple use of Ohm's law here. Now you substitute those numbers, and calculate. Remember that the internal resistance must usually be really small. So in case you get numbers like million and thousand and all that, just take a second look at it, because the internal resistance is supposed to be a real small number. So then that brings us to the last question. You have two bulbs connected in parallel. You have to find the net resistance. So let's first find the resistance of each bulb using the formula for power. So that is the resistance of the first one. Then likewise you find the resistance of the second one. And since they are in parallel, the equivalent resistance is given by R1 R2 by R1 plus R2, which is the same as 1 by R1 plus 1 by R2. Which gives you 105.22 ohms. Thank you and good luck.